Okay, 2011 AIME, this is problem 5 from the AIME 1, and it says the vertices of a regular nonagon, 9-sided polygon, are to be labeled with the digits 1 through 9 in such a way that the sum of the numbers on every 3 consecutive vertices is a multiple of 3. Two acceptable arrangements are considered to be indistinguishable if one can be obtained from the other by rotating the nonagon in the plane. Find the number of distinguishable acceptable arrangements. So first, let me sketch a nonagon. So 9 sides, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a lovely nonagon, almost regular. Okay. And for simplicity's sake, I will label the vertices, so I don't need to draw any more nonagons, but we can just talk about the vertices: A, B, C, D, E, F, G, H, and I. And here's the idea, okay? What's going to happen is I'm going to need to put down some numbers, but I need to make sure that every group of 3 consecutive vertices will add up to a multiple of 3. And here's how we can do that. I have the digits 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And those are going to be equal to mod 3. Okay, so we're taking out all of the 3's because that's every... now leave us just the information needed to see if we have a multiple of 3. So 1, 2, but 3 mod 3 is 0. 1, 2, 0. 1, 2, 0. And here's the idea. If I add any of the 1's to any of the 2's to any of the 0's, I will get a multiple of 6. For example, 1 plus 2 plus 3 is 6, it's a multiple of 3. If I add 2, let's say 4, it's multiple, it's a 1 here, plus 8 is 12, plus 6 is 18, that's still a multiple of 3. So what's going to happen is this. I'm going to need the A, the D, and the G to represent the same number mod 3. I'm going to need, and I'll explain very shortly why, B, E, and H to represent the same number mod 3. And I need C, F, and I to do the same. And the reason is this. If I look at these 3 consecutive numbers, they must be a multiple of 3. But if I look at these 3 consecutive numbers, they must also be a multiple of 3. And so when I lose A but gain D, I have to have the same sort of change in the multiples. I need to have A and D be in some ways the same so that I still have a multiple of 3. And I get that by having it be the same number mod 3. Okay, so here's how we're going to do this. I have these. And so I have A, B, C, D, E, F, G, H, and I. And I'm going to automatically set this as not just one mod 3, but the number 1 itself. And the reason that I'm going to do this, so there is no choice here. It is 1. And what this does for me is, if one can be obtained from the other by rotating the nonagon in the plane, well, I can always rotate the nonagon so this 1 is sitting at the top, and that'll take care of all of my rotations. But this means that then D and G must be 1 mod 3's. Okay? And there are 2 ways that I can get the other ones to work out. I can say, okay, let's let B be 2, which means E and H have to be 2 as well, because if I look at B, C, D, or C, D, E, the B and the E have to act the same in many ways. And that leaves me with 0 for C, F, and I. That's one choice. I could similarly still have 1 with no choice to it. It has to be the number 1, not just 1 mod 3. And 1 for D and 1 for G. But I could decide to have B be a 0 mod 3. And I could choose to have C be 2 then mod 3. So this is also valid. And here's what we're going to do with this. I have no choice here, so I only have one choice for this, the number 1. But I have 3 numbers that are 2 mod 3, so I have 3 choices for this, 2 choices left for this one, 1 choice left for this, 2. Same with the zeros. I have 3 zeros, so I start off with 3 choices, but once I've chosen one of these, either 3, 6, or 9, then I only have 2 choices left for this 0, 1 choice left for this 0. And I chose, this had to be 1, okay, so this is taken out of the mix. I only have 2 ones left, so I have 2 choices for this one, 1 choice for this one, which means that this is going to be 3 factorial for the B's, 3 factorial ways to arrange those, 3 factorial for the C, for the O, for the zeros, so 3 factorial for 2's, 3 factorial for the zeros, but only 2 factorial for the 1's, which is going to be 6 times 6 times 2, which is, of course, 72. This can be counted in the same way. I'm just going to sketch it quickly. 1, 2, 1, 3, 2, 1, 3, 2, 1, which also has 72 ways that I can arrange them in this order. So my final number of distinguishable, acceptable arrangements is 2 ways to arrange things where I have 72 options. So I have 144 distinguishable, acceptable arrangements, and that's the answer.